Hey, welcome back. This is calculating chi-square goodness of fit in R, following up the videos 5.2 where we did it by hand and 5.3 where we did this in Excel. I already have a script file put up that you will have shared, and I'm just going to walk through some of the functions that we have here and show you what's what. So the first thing we're going to do is we're going to enter a vector of data that has all of our called students, A, B, C, D, and E. I'm not going to worry about assigning letter names at the moment because we just really want to get to the core of the test. If this was part of a larger data set with other variables, then yes, I would have a column for how often they were called and the students' names as well. So we have that in there. How frequently were these students called? And we can see that they were called 25 times. The expected chance of being called, but by the way, we're doing a lot of this by hand because R's goodness of fit is a little bit different when we need to still set up how often they were called and things like that. So we're just taking it piece by piece. So if you just do 1 over the total number of times they were being called, the length is that vector command, that's going to tell us 0.2, 20% chance, or 1 over 5, which is the expected amount that we had from when we were doing it by hand. 5 students should expect to be called, if equally, 1 out of 5 times. So we're going to make another vector here that shows how often should they have been called, and I'm going to call it call.e. Again, these names are just arbitrary, and I'm trying to get names that have something to kind of do with what I'm working on here. So we start with a C function making a column of data, rep function nested inside there, so we're going to be repeating something. So we are repeating the 1 over length call, so we're repeating that 0.2 value. I could have just typed in 0.2 right here, but I just want to show this being nested, comma, and then the rep function wants to know how many times are we repeating. We are repeating by the length of the call variable there. So the length of the call variable is going to be 5. This could have been rep 0.2 comma 5, and this will give us the same thing, but I'm just going to go ahead and run that. So then if we go ahead and look at the call E variable, it shows us we have a vector of 0.2 that's being repeated 5 times. Now in order to go ahead and calculate the chi-square goodness of fit in R, we're going to use the chi-sq dot test. That's the function, and then we need to specify an x equals and a p equals if you want to just make sure you don't have any accents. You don't need them, but it will help you. So we're going to specify that x equals the name of the variable that has how often the students were called, and then p equals the name of the variable of how frequently, or the probability that they should have been called. Rather, not frequently, probability. So we have chi-sq.test, call, and p, and that's going to show our reported chi-square test results in the output console below. The chi-square statistic obtained is 7.2 with 4 degrees of freedom and a p-value of 0.1257. If you recall the video from how to do this in Excel, the numbers match exactly. A little bit of rounding on the p-value is expected. Now, just like as R is an object-oriented program, I can run this and store my chi-square test as its own object. When a chi-square test is stored as an object, as will many different tests that we will be running in this term, those objects have attributes. If you look at that object with the attributes function, it shows us a variety of different names or values that are stored inside of there. These are the same values that R is using to give us the output results that we have there. We have things like statistic, we have things like p-value, and other values that haven't been shown. But what I want to show you more is the qCHISQ function. This qCHISQ function is what will give us the critical value. So we plug in 0.95 because we are looking at the upper end of the chi-square distribution, with df equaling what I called call df, or it would be 4. And that will show us, oh, I actually didn't say that yet. Let me go ahead and just change this to 4. And that's going to show us that the chi-square critical value is 9.48. And extra values. 9.48, which you may recall was the same critical value we estimated using the critical value table from the Excel formula. So then what I have here is just some extra lines of code that I can use. It's the ones I use to show the chi-square result in distribution curve in the 5.2 lecture slide. We're not going to go through all of the different lines line by line, but there's a section where I set up some of the additional values I need. There's a spot where we actually plot the curve itself. And then we can go ahead and add a section where we create the shaded region under the curve. And then we have a spot where I can add in where we have the value obtained. And then a spot where we can add in the actual number values on that curve. And when I click zoom, there it is. We can see that here's our distribution of the chi-square when we have 4 degrees of freedom. The shaded region showing when we have the critical value at approximately 9.5. And the dotted blue line showing the chi-square value we obtained at 7.2. And we see that indeed the value of 7.2 is not within the red critical shaded region of this particular curve. It is not statistically significant.